So in chapter 15, there was one last little bit I wanted to mention that relates to what we're going to be doing in chapter 16. And that is, if you think about harmonic motion, okay, so we got a mass on a spring right here. It's going back and forth, back and forth, back and forth. And so if you look at it, the x is going to be equal to some amplitude cosine omega t. We know the v is minus a omega sine omega t, and we know that a is minus a omega squared cosine omega t, and we know that's equal to minus omega squared times x. And so you look at that and say, now wait a minute, what's omega? Omega is v over r, so that means this is v squared over r squared x. And so you look at that and think about it and say, well, wait, let's stop and think about this just a moment. Okay, and so x is going to be like your r. So because we need to figure out what is omega squared. So let's leave it at omega squared for right now. Okay. And so these are all things that we had derived here for this. Okay. For a mass on a spring. Okay. And we look at it and we say, now what about a mass here going in circular motion? Okay, so we're going to call radius r, this thing's going around. So as it's going around here, theta equals omega t. So it's going at constant angular velocity. And if I just look at the x component of that, the x component of the position is going to be r cosine omega t, and the velocity is going to be minus r omega sine omega t, and that's the x component of the velocity, and the x component of the acceleration is minus r omega squared cosine omega t. Oh, that's the same thing if a is r. So, in other words, we can even go one step further. We can talk about the centripetal force right here. And the centripetal force is going to be mv squared over r, right? Okay, well, we just said that for circular motion, okay, so this is for circular motion, okay, but for the rotational motion, okay, or mass on a spring, then we found that, F equals ma, so that would be m times a, and we said that a was going to be equal to v squared over a times x. Okay, well, wait a minute, a squared, but if a is r, that cancels, and same thing. Okay, and so lo and behold, what that means is that when you are looking, if you're standing here looking with your eye at something going around in circular motion, you're just seeing it go back and forth as harmonic motion. And so this almost suggests that harmonic motion can be described of as circular motion. Okay, and in fact it can. It does mean the harmonic motion is described as circular motion. In fact, that's one of the things that we do. We imagine if we got a mass here K1, and then we have another K2, and then a mass on the end of that, and it's moving. That's not simple harmonic motion, but what we do is we imagine that we've got something going around here, some theta 1, and then we got some theta 2 right here, and these two things are going around where theta 1 equals omega 1t, theta 2 equals omega 2t, okay, and we have a radius amplitude 1, amplitude 2, and so the total amplitude is going to be a1x plus a2x, and if you do that, it actually works. And so we call these phasors, okay, and we call this a phasor diagram right here. And so even though it's not really happening, even though reality is just the x component of that, okay, and again, that's what we're doing, where you're saying that it's as if something is moving, and as it's moving, we have x and y, so it's in two-dimensional motion here, okay. This is real, and this is imaginary. It's suggesting there's actually, that this real motion right here, that's the universe that you see. This is perpendicular or orthogonal to the universe that you see. Now, what does that mean? Well, what's orthogonal to the universe? Is that actually existence, or is it non-existence? Or is there maybe more to the universe than you see? Is there something more than three spatial dimensions and a time dimension? Are there other dimensions? Is there a bigger universe or a multiverse or something beyond what you're experiencing? That's getting into the metaphysics of physics. And so, but it does suggest there's more to things than what you see, and that's a very fascinating sort of thing to get into. And so this is a relationship now between rotational motion and simple harmonic motion. The simple harmonic motion is just one component of the circular motion, and so the circular motion is in a plane that's orthogonal to the universe, and so the x part is the real that's in the universe, and the y part is orthogonal to the universe. And so we can imagine this as being a phase diagram in which we are only able to experience the real component. So that's another way of looking at this, and it turns out mathematically it makes solving some of the problems for non-simple harmonic oscillators a lot easier to do. And so that's why we use this technique, and we use it in physics 2 as well to solve electrical problems.